we're going to start with today's talk. Today's speaker is Baibhab Karmakar. He worked in ISL Pune and he has worked on seismic information. He will introduce his work and start.
Hello everyone, good evening. So let's start my work. I am Baibhab Karmakar and I work in ISL Pune on the surface wave amplification. So let's begin. As we all know, we are just 500 kilometers away from the Himalayan part and it is very north to us. So we can think that in the Bengal basin, where we are now, it is 500 kilometers away from the Bengal tectonically active, Himalayan tectonically active region. We may assume that we are safe there. But is it the case that like 500 kilometers gives us the clean sheet to build higher buildings or something? So my work was to find is it really the case whether the seismic attenuation or any kind of geometrical spreading can reduce the effect of surface wave in the Bengal basin. To answer that, I went here and worked with Arjun Datta and he gave me the topic and it's about seismic wave surface wave application in the Bengal basin where we are right now. So this is the basic question. Main agenda will be like what is the main hypothesis behind it. Then we will go through the methodology and study area. Then how will what are the tools we have used. Then at the end we will see the implications and future also. So coming to the hypothesis part, as you can see, if a seismic event happens or a faulting happens, the body wave and the surface wave travels through various mediums, and the Himalayan region is consists of hard rock. Consists of hard rocks. So in the hard rock, due to the various equations, we know that the velocity of any seismic waves is very high there. But what about the sediment layers? So in the Bengal basin area, we have almost 20 kilometers thick sediment basins. So if a seismic wave enters into those 20 kilometer thick sediment layers, what will happen to them? So we have found out that the velocity, the seismic wave velocity decreases. To maintain the energy or conserve the energy, the surface wave gets amplified. This is the main hypothesis we are proposing. So let's see is it true or not to the process. Okay. So for this we have used a seismic event of 2012. As you can see, this is marked here. This event happened in 2012 and the seismic waves travel in the great circular path. And we picked out two stations. One is in the hard rock region and one is in the Bengal basin region to see if there are any kind of application which may concern us. We have carefully picked up two stations, as if we miss the dead circular path, we have to do some component analysis. So we are just want to avoid that. So we have chosen these two stations which are almost in the dead circular path. One is this one and one is this one. Okay. So this is my study area. As you can see, there is a fault here. Yes, this fault is called Rocky fault, and on the top of it we can see the Serum plateau. So what is special about this Serum plateau? This Serum plateau doesn't have too much sediments, as it's a hard rock region. So our first hypothesis where we assume that for the hard rock region we should expect a lower amplification than the basins. So we picked out a station which is actually at Shillong, in the Serum plateau. And another station we picked out is the Agartala, which is here. It is fairly near to the river Brahmaputra, and this is in the basin doesn't mean that it should be only in Bengal, it can be in Bangladesh too. It is in the almost near to Bangladesh. So this is sediment station, and this one is the that are hardware stations. So what about the discontinuity? We'll come to this later. Why we are using this discontinuity and why we are stressing on this term discontinuity here or any fault here, the locky fault. We'll see later. So coming to the next. So my main methodology to verify whether it's any whether if there is any amplification or not, we actually used very simple 1D velocity model which varies with depth, like for various depth and other terms. The velocity of the S wave and P waves and the density varies. So we use those 1D velocity model data to and use some mathematical tools like Green's function and all, and use some computational knowledge to model and predict whether it will be a amplification or not. For this, we have used this HWRT model, which is developed by my supervisor. His name is Arjun Datta. So this is a semi-analytical package which actually uses this 1D velocity model and discontinuities to predict any kind of amplification. And how do we define amplification? We will see in the next slides. And there is a well-known software called SpeckFilm 2D simulations. This uses a full waveform solutions, like we just create some model with different mesh sizes, mesh in the sense with different resolution, and for each resolution it solves the wave equation to find the end result of a seismic event. So this is our main prediction procedure. Then at the end we just matched our predictions with the observational things. So coming to the next slide, this one is actually the amplification factor to see whether the seismic waves, mainly the surface wave, I have worked in the surface wave region, whether the surface waves gets amplified or not. We have defined a term called transmission ratio. We didn't define this term. It is defined by some other professors in their research work. This is simply just the ratio of the amplitude of the transmitted ray and divided by the incident ray. Why we have used this ratio? This is because to normalize things, normalize in the sense if we use any subtraction and all, then there will be some error which will get like in the values. So you use this the division to see the waves amplification in terms of multiples. So yeah, let's talk about the SWRT. What does it do? So SWRT is a very simple and lightweight package which uses, I actually explained it earlier, like uses 1D velocity model, and if there is a discontinuity in between two 1D velocity models, it will just calculate the amplification or the transmission ratio based on the 1D velocity model. So there are some mathematical background here, we are not going into that. So there is an example here. As you can see, there is a 1D velocity model with all the velocities and the depth. And if we transmit any kind of surface wave from this side to this side, this is we are calling forward transmission, then we can see a discontinuity there. So what should we expect here when the wave crosses this discontinuity? This is what this SWRT calculates. So this for this model, this is the end result. Oh, one more thing is that when this discontinuity hits, when the surface wave hits this discontinuity, there are some normal changes. I mean, if the fundamental mode of the surface wave hit the discontinuity, this model, we can see this is the mode 0, this is the fundamental mode, but you can also see some minimum amount of higher modes. This is for the random waves, but in random waves is very small, but in case of the last wave, we can see a significant amount of higher mode for the mode 2 and 1. So these high mode conversions are very crucial factors for modeling and predicting those applications. So coming to the spectrum 2D, as we have explained, it just uses element status and material properties to calculate and solve equations. Like we can actually create a mesh out of my velocity models and run a simulation. It is very computationally heavy and takes some time. If I model a outcrop or a region of 400 km and the mesh size is very low, then it can crash some computers. So for that we actually use HWRT. But spectrally, why we have used is that to verify our HWRT results, as it is very lightweight and it is not well established by now. So we use this spectrum 2D to verify whether our results are correct or not. Let's come into the velocity models. So this is the most important part of my research. As you can see, the medium one is the black one. You can see that the VS velocity is greater than 3.5, which actually says that it is not any kind of segment layer or something, and it is a hard rock layer. But as you can see, for the medium 2, there is a continuous low S velocity zone up to about 25 kilometers. So this is the thick segment layer of which I am talking about. So this is the actual models of those regions. Like medium 2 is the Agartala, which I have shown in the map, where it is situated in the Bengal basin, and the Shillong velocity model, which is situated in the Arjun region with the Shillong plateau. We can see that after 40 kilometers of depth, you can see it crosses 4.2 kilometers per second using velocity layer, which actually says it's the MOHO, and they are kind of similar. So after that, we used a general PREM model to match the stressor, to create the overall velocity structure. As the after MOHO, we generally don't see any kind of variation for other regions. Yes, we can see some variation, but in a zone where the radius is too small, this can vary, but it can affect our results. So, for my model, for these two quantity velocity models, I have run the HWRT package, and these are the results. As you can see, this is for the lava wave, the surface wave, which actually has the transverse component. You can see that the modes in the fundamental mode after transmission, the transmission ratio and the amplification factor is going up to 6 times. That means if we provide some surface wave to the Shillong plateau, and if it travels through the discontinuity of the Loki fault, and we record the result in the Agartala station, we should expect an amplification of 4 to 5 times. So
this is for one particular station, right?
yes.
Which station?
This is not for particular station. This is for the pair of stations. Like
your stations are one grid structure.
what?
One grid
Yes.
structure.
Two stations.
Two stations can't be on the same pressure.
What?
Those two stations are not on the same pressure.
Yes, it is.
Every question at the end, like,
So I was telling that this is the model which we use. This is the discontinuity, and for the sake of security, you can see that you can assume that here is the Shillong plateau and another alternate is here. So these are the two stations. Based transmission ratio. As transmission ratio is defined by the ratio of the transmitted wave and the incident surface wave. So we have to use two stations, otherwise we cannot get any kind of transmission ratio. It is as it is defined by two stations. So this is the amplification we are getting here for the log wave, and we expect some amplification for the dial wave, where it is about 1.75 times than the incident record. So let's come to the real data analysis part, for which we have actually compared the results. Yeah. This is for the log wave part. As you can see, this is a normal amplitude spectrum. For this, I am just telling how I have calculated the spectrum. We have those velocity seismogram or waveforms, then we have changed it to displacement seismogram, then applied some filtering, frequency filtering to separate out the surface wave from the body waves, and then actually doing a Fourier transform, we have got this amplitude spectrum. So for the both station, for the same article, we have analyzed the both stations, like for the essential and the Shillong and the Agartala. So we have the same event and two stations and analyze the waveforms. So when we have calculated the amplitude spectra for the Agartala, which is marked with blue, and we have calculated it for the Shillong, which is marked with red. As you can clearly see, for the frequency band of 0.001 to 0.015 Hz, we can see that the blue band is kind of higher than the red ones. Here we can actually see the amplification which are actually happening here. Then we have applied those transmission ratio calculations and calculated the transmission ratio by dividing the Agartala amplitude and the Shillong amplitude. So this is the transmission ratio of the real data. As you can see, this is going up to 5 to 6 times. So if we compare it with our SWRT and the spectrum results, what we can see is this. This is actually my final result. The red dotted line is the sum of the all nodes of the SWRT results of the transmission ratio, and the green one is the spectrum result. Spectrum is just to verify whether the SWRT results are actually good or not. And this blue line is the mean moving average of the real data of the transmission ratio. As you can clearly see, this blue moving average is kind of following our predictions, right? And the predictions are going up to 4 or 5 times transmission ratio, and it is going well with our real data. This is for the log wave. And same we have done it for the rally wave part. For the rally wave, same calculation, same analysis we have done. Like for Agartala, this is the blue one, and for the Shillong, this is the red one. And you can clearly see the blue one is higher than the red one, and calculate the transmission ratio. So here is the comparison plot with the SWRT and the spectrum. But here is a catch in the rally wave. Like we're still figuring out. But we can see that there is a small peak of the SWRT plot in the transmission ratio at about 0.02 Hz. But in the real data, the peak is coming later. So we don't know what is the reason. So here comes our future works, what we can do about it to find whether it is the real, is it the real pattern, or it is just for the error of the data. So we'll do more analysis on these things. Like there are several stations, one is in the hard rock regions. We can get the data and analyze it, by the same mechanism. So we can use some kind of taking the mean or median to see whether this SDO results is true or our observed data is true. So coming to the results, this is our result that we can see for the transverse comfort, I mean for the love wave, we can see 5 times amplification in the hard rock region in the frequency range of 0.01 to 0.15 Hz. So for the vertical comfort, where we have analyzed the Rayleigh wave, we didn't have much data and the results are not good. We are working on it. Hopefully, we can go with our flow. So that's it for my presentation. And another thing is that we are not in the safe zone. We are kind of in the risky zone. Like as the sediment doesn't, the basin doesn't always hold only the sediment, it also holds the risk and amplifies the risks. So that's it. Thank you everyone.